Hello and welcome to Lecture 28 on Taylor series. So in this lecture, we're going to be taking the idea of power series and we're going to be looking at a very specific form of the power series, which we call Taylor series. And later, we're going to be talking about Maclaurin series as well. So we start with f of x. It's going to be any function that can be represented by a power series. So f of x is equal to the sum from n equals 0 to infinity. These c sub n's here are the coefficients for each term in the series. And then this a right here, x minus a, this a is called the center. So we're going to be calling this the center of the series. And this formula will hold as long as x minus a is, the absolute value of x minus a is less than r, where r is our radius of convergence. And we've talked about this radius of convergence from our last few lectures. So that's what the capital R stands for here. So it would be nice to figure out some sort of formula for the coefficients of a power series that looks like this. So that's what we're going to be doing first. So we're going to look for a general formula for c sub n. So first thing I'm going to do is I'm going to go ahead and write this out. So if I were to write out the first few terms of this infinite series, you'd plug in n equals 0, for example, and you would just get c sub 0 if you plug that in. For n equals 1, if you plugged in that, you'd get c1 x minus a to the first power. Continuing, you'd have the second coefficient, x minus a to the second power. I'll continue with a few more of these. So x minus a to the third power. I'll do one more. I have the fourth coefficient, c sub 4, x minus a to the fourth power. And this continues forever. So this is what this series looks like if you expand it out by plugging in values for n. And now let's first look at the value of f at particular derivatives. So when we plug in a. So first I'm going to look at, well, what is f of a equal to? Well, if I plug the center into the function f here, notice all these terms go to 0 except for the first one. So f of a is c sub 0. Then if I look at the first derivative of f of x, this c sub 0, this coefficient, would go to 0. And the first derivative would be equal to c sub 1. And then here I would do the power rule and bring the 2 in front. So I'd have 2 c sub 2x minus a plus, and continuing doing the power rule for each of these terms, the derivative would give me 3 c sub 3 x minus a to the second plus 4 c sub 4 x minus a to the third. And again, this would continue forever. But these are the first few terms of the first derivative of f. And if I go ahead now and evaluate at a once more, notice all of these terms go to 0 except for the first one. So f prime of a would be c sub 1. And I'll do a few more of these. So the second derivative, if I take the derivative of this right here, I would get 2c2 plus 3 times 2c3x minus a plus 4 times 3c4 x minus a squared. Again, this continuing forever. And if I follow the same idea, if I plug in the center a into this expression, I get 2c sub 2. And if you continue on with this one more time, I'll just do one more. I have the third derivative of f of x would give me 3 times 2c sub 3 plus 4 times 3 times 2 c sub 4 x minus a. Kind of running out of things now to take the derivative of. But if I finally evaluate this at a, I will get 3 times 2 c sub 3. And that's what f triple prime at a is equal to. So I'm just going to say this pattern continues. And the pattern that you should notice is that the nth derivative at a is equal to n factorial times c sub n. Because with each additional derivative, I get another factor for that factorial. So here at the third derivative, I had 3 times 2 times 1, and this will continue. So this is the formula that I can get from this process. And in other words, that means that the c sub n, the coefficients, are equal to the nth derivative of f at a divided by n factorial. So that is the formula for these coefficients of the power series. So this leads us to this theorem over here. So if f has a power series representation at x equals a, so we call this the center, then f of x is equal to summation n equals 0 to infinity c sub n times x minus a to the n. And this is true as long as we are within the radius of convergence here, so I'll just make a note of that here. And these coefficients, these c sub n's, are given by c sub n is the nth derivative of f at a divided by n factorial. And so therefore, we could re-express this power series representation that I started with the following way. So you could say, well, this is equal to summation n equals 0 to infinity, and replace the c sub n with the formula we just found. So replace it with the nth derivative at a divided by n factorial x minus a to the n. But then if you write out the first few terms of this, so for example, if you plug in 0, you would get f of a plus the first derivative at a over 1 factorial x minus a to the first power. And you could continue this. You could plug in this n equals 2, and you would get f double prime at a over 2 factorial x minus a to the second power. And this sort of just continues. So this is what the power series representation looks like if you expand it out a bit. And then just a quick note, because we're going to be dealing with this a lot, when you choose your center to be 0, that has a very special name for the series. So a series centered at 0 is called a Maclaurin series. So when we say Maclaurin series, that's all we mean, is that we mean that a is 0 for that particular Taylor series. So now, let's look at an actual function and try to find its power series representation, its Maclaurin series. So we're going to find the Maclaurin series. And remember, this just means that the center is 0. We're going to find the Maclaurin series for f of x equals e to the x. And we're going to find its interval of convergence. So what are we doing here? Well, if you look at the formula, we're going to need a lot of derivatives. So we're going to have to figure out what this expression is for this particular function right here. So a good strategy would be to start getting all your information together. So what I'm going to do is I'm going to list, for a couple of n values, what's going on with the nth derivative. And then I'd really like to know what's going on with the nth derivative at, and this time it's a equals 0. So I'd like to get a handle on what's going on here. So we'll do just a few. We'll do 0, 1, 2, 3. We'll do capital N down here as well. And let's think about what is the 0th derivative of f of x. Well, that's just f of x. That's e to the x. And what's really nice about this one is it doesn't matter how many derivatives you take, the first derivative, the second derivative, the third derivative, they're all e to the x here. So in this column, any derivative is going to be e to the x. And what happens if you plug in 0 into any of these derivatives? Well, you get 1 for all of them. So what happens in this case is you have e to the x it's our f of x. So by our formula, this is the summation n equals 0 to infinity. And then here's our formula for the Taylor series representation. So I need to know what is the nth derivative at a, and this time my a is 0. So my nth derivative at a is going to be 1. That's what it is right here. That's what it is for every single derivative. So we have fn at a is 1. And maybe I should make this a capital N, because that's the N I'm plugging in. So in general, it's this. So this right here, this portion is just going to be 1. Following the formula, you divide by n factorial, and you multiply by x. My a is 0, so I don't need to plug that in to the n. And if I just write that a little nicer, that means that I have the summation n equals 0 to infinity of x to the n over n factorial. And this is the Maclaurin series. This is our very first one that we're learning. You're going to need to know quite a number of these standard ones, but this is the first one on our list. So I'd make a flashcard for this. Maclaurin series for e to the x is this. And now I'd like to know, what is the interval of convergence for this series? And what I could do is I can go back to the ratio test to figure that out. So let's apply the ratio test. So what I'm going to do is I'm going to say the limit as n goes to infinity. And this is going to be my a sub n here. So I want the absolute value of a sub n plus 1 over a sub n. Well, if I plug this in, I'm going to get the limit as n goes to infinity. And this is going to be absolute value of x to the n plus 1 divided by n plus 1 factorial divided by x to the n over n factorial. And I'll continue down here. So if you simplify that quite a bit, you're going to get the limit as n goes to infinity of the absolute value of x over n plus 1. So that's what's going to happen, because you'll have all of these for the factorials here will cancel, except for you'll have the n plus 1 remaining. And all of these x's but 1 are going to cancel out here. N is a positive number, so that can come out of the absolute value, but you have 1 x remaining. So this is what we're looking at. So simplify that if you need to. And we're asking, what does that equal to? Well, if you choose any x value at all, any real number x, the denominator goes to infinity, while you pick any finite number here. So for any real number x, this goes to 0. This is 0 for any real number x. It doesn't matter which one you pick, because the denominator is going to go to infinity. Once you've picked a finite number here, this will go to 0. So that's true for this. And then remember, when this expression goes to a value that's less than 1, we say that the series is absolutely convergent. So that's true for all x values. So it means our interval of convergence, then, is going to be from negative infinity to infinity. Because this, no matter what x is, it will always be less than 1. Using the ratio test, we know that that will converge absolutely. So not only do we know that e to the x has this series representation, but it's valid for every single x value you give me, all real x values. OK, in the next part of this video, we're going to be taking a look at sine of x. We're going to be doing a very similar exercise with that, and then also doing a few applications with the Maclaurin series for sine x as well. So I'll see you for that in just a moment. All right, so let's finish up this video by doing another Maclaurin series, and this time for sine of x. So this is going to be another one of those main Maclaurin series that you're just going to want to have memorized. Again, so once we prove this, you might just want to have the note card for what the Maclaurin series is. Then after that, we're going to do a couple applications with the Maclaurin series that we didn't actually do with e to the x last time. So we're going to find the Maclaurin series for the function f of x equals sine of x. And remember, if it's a Maclaurin series, it's telling you that the center, A, equals 0. And I'm going to start the same table I did last time for the e to the x example. And we'll start filling in n values. So you start at 0. And I'm going to go down to 4. Now this one's going to be a little more complicated than the first example. I can't just give you that example and then give you a more difficult one on the exam. So what we're going to do is we're going to work our way up to more difficult and difficult examples, OK? So this will be slightly more difficult than the e to the x example. Now, I need to start taking derivatives. And when n is 0, the 0th derivative is the original function. So the original function is sine of x. And if you evaluate that at the a that we're given, which is 0, sine of 0 is 0. And I'm going to just fill out the next few rows here. So the derivative of sine is cosine. That's my first derivative. The second derivative would be negative sine. The third derivative would be negative cosine. And then the fourth derivative would be back to sine of x again. And I know at this stage, this is just going to repeat. So I'm OK stopping here. And then if I plug in 0 into all of these, I get 1, 0, -1, 0. The goal here is to kind of establish a pattern for what's going on so we can describe this in general. So the formula that we're looking at here is f of x is supposed to be a series from n equals 0 to infinity of the nth derivative of f at a divided by n factorial times x minus a to the n. OK, so I'm switching colors here. I'm trying to see if this one will show up better. That looks pretty good for me. Hopefully it doesn't die. So remember, we wrote out what this is. This is simply f of 0 if I plug in n equals 0. Then if you plug in n equals 1, it's f prime of 0 divided by 1 factorial. If you plug in n equals 2, you would get f double prime of 0, 2 factorial. I'm missing the x right here, right? Because you have, if you plug in n equals 1, you have this x minus a, but here a is 0. This one would be x squared. Let's do one more. You'd have f triple prime at 0 divided by 3 factorial. And this would be x to the third power. And this continues, right, if you were to expand this. So what I'm going to do is I'm just going to start filling in what I have. So f of 0 is 0. So this first term is 0. F prime of 0 is 1. So in this spot, I have 1. And then, if you notice, the second derivative at 0 is also 0. So the observation that you should be making here, the observation is every even power, not even even power, but every even n value results in f, the nth derivative at 0 will be 0. So what happens is we lose every single one of the even power terms, right? So we do get this one. We lose the second one, actually, right? We lose the 0, the 2. We get the third one, though. That's -1. So we would get -1, and this would be x to the third, 3 factorial. If the pattern continued, the next one we would get would be the fifth one. This would be plus 1 over 5 factorial x to the fifth, right? And this would keep going on forever. So we would have all of our odd-powered things are remaining. I've left off an x right here, but go ahead and fill that in. That x came from here. It's the same x I left off earlier. I don't know why I keep leaving that off, but this x goes here. So notice for the sign here, you have all of your odd powers are remaining. Well, what's a way to re-express this? Well, you could say, well, I have the summation n equals 0 to infinity. And I have an alternating series. So the sign is going to keep switching based on whether I have 1 or -1. And then what's happening in the denominator? Well, I keep the odd factorials. So this is going to be 2n plus 1 factorial. And I'm also keeping the odd powers of the x's. So this is x to the 2n plus 1. So this right here is our Maclaurin series for sine of x, because if you were to check with this, this expression right here will keep all of the odd powers present, and then all the other ones go to 0. So this would be another thing I would make a note card out of. This one right here is our Maclaurin series for sine of x. Now, a question I'm going to leave for you is, just like that other example I did, what is the interval of convergence? So the answer to that is actually The answer is negative infinity to infinity. So just like with the last example, you should try that as an exercise. You should take this, use the ratio test, see if you can prove that the interval of convergence for this Maclaurin series is also negative infinity to infinity. So now what I'd like to do is I'd like to take the fact that we know this now and apply it for these three examples right here. So the first one says, use a second degree polynomial to approximate sine of 1. Well, actually, what I'm going to do is change this to a third degree polynomial. That's what I'm going to do. So I'm going to say this is a third degree polynomial because I'm just looking at the polynomial that we got. So if I'm using a third degree polynomial, then I'm going to be using just these first two terms of the Maclaurin series. I'm going to be using these two because this goes up to a third degree polynomial, and I'll stop at that point. So instead of x here, I'm going to have 1. And then I have minus 1 over 3 factorial. And then I plug in a 1 for this x right here. So sine of 1 is going to be approximately these first two terms right here where I plug 1 into it. And then what is that? That's 1 minus 1 over 3 factorial is 6. So that's 5 over 6. So normally if I would ask you what is sine of 1, you would look at me kind of weird because that's not a unit circle measure, right? But now what we can do is we can get a pretty close estimate. The thing is, the more of these terms that you take, like if I had asked you to go to a 5th or a 7th degree polynomial, it's going to be a better and better estimate if you give me more and more of these terms. And this is already pretty good, actually, if you use a calculator and check that. Remember, we have the alternating series estimation. So what I'm going to ask now is, how good of an approximation of sine of 1 did we get? So we're going to find the maximum error of this approximation. If you recall from our alternating series estimation theorem lesson, the maximum amount of error that this produces in the true sum is the magnitude of the next term. So what we need to do is we need to look at the next term. And our next term in the series is this one, the one we didn't use. So this is the first one that we discarded. And what I need to do is I need to plug 1 into that. So we're going to let x equal 1. So then we get 1, the absolute value of 1 over 5 factorial 1 to the 5th power. I'm plugging in 1. That's equal to 1 over 120. So this represents 1 over 120 represents, and now this pen is dying, of course, represents the max amount of error in the previous approximation. So this approximation of 5, 6 is actually at most off by 1 over 120, which is a pretty small amount to be off by. OK, and then this last example here, now I'm saying, OK, well, what if I want a second degree polynomial for sine of x, but I want to center it somewhere else? So as soon as I get a working pen, I'm going to come back to this. All right, so I'm back with a pen that I think might work. We'll see. So we are changing the center from being at a equals 0 to pi over 6. So this Maclaurin series that I worked with actually will not apply anymore. I'm going to need to make some separate calculations for this. The good thing is I'm not calculating an entire Maclaurin series for this one like I am here. What I'm doing here is I just need a second degree polynomial. So I just need to compute a few of these, and I'm going to center this at pi over 6. So here's what I'm going to do. First, I'm going to start listing out my 0th derivative, my first derivative, and my second derivative. I'm going to just be very organized with this. So we start with sine x. Our first derivative, I can just copy that column over there. Honestly, it's cosine of x. The second derivative is going to be minus sine of x. And now my center has shifted to pi over 6. So what I need to do is I need to evaluate all of these at pi over 6. So you're going to see that these aren't going to be zeros and ones anymore like they were over here in the third column. You're going to actually get values for all of these. So So we're going to, instead of deleting the even terms over here, even powered terms, you're going to keep everything. So f of pi over 6, got to use my hand trick here, it's 1/2. And then cosine of pi over 6, that's root 3 over 2. And then that makes negative sine of pi over 6, negative 1/2. So now I just need to recall that the general formula for the Maclaurin series, if you write it out, or not Maclaurin series, I'm sorry, Taylor series, this time it's just a Taylor series, you have for that general formula, it's f of a, so we're going to say this f of x is f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a squared. And it does keep going forever, but I just want a second degree polynomial. So now I just go ahead and I fill in what I have here. So because we get to stop at a second degree, I just need to fill in these 3 pieces of information. So this time a is pi over 6. So f of a is 1/2. Then I do plus f prime of a, which is root 3 over 2, divided by 1 factorial doesn't change anything. And then minus, I have x minus pi over 6. And then my last term, I need to make a second degree polynomial. F double prime of a is actually negative 1/2, and I'm going to divide that by 2. So I'm just going to get negative 1/4 for this coefficient, and then it's x minus pi over 6 squared. And we're going to stop right there. So f of x is going to be approximately this, because we've stopped at a certain point. And this will be the Taylor series centered at pi over 6. OK, so there were some applications of using the Maclaurin series and also finding a series that's not centered at 0, which you can do as well. In the next video, we're just going to be doing more practice and more applications with Maclaurin and Taylor series. So I will see you then. I like this pen. I hope this pen works for the next video too. Send me any questions you have, and I'll see you next time. Bye.